In this video, we will discuss the problem peak element. Previously, this problem has been asked in companies like Amazon and Google. So let's read the problem statement. Problem says that we'll be given an array where no two adjacent elements will be the same, and we have to find the index of the peak element. Now, an element is considered as a peak element if it is greater than its element on the left side and the right side if they exist. Okay, there can be multiple peak elements that can exist in an array as well. In such a case, we can return any index of the peak element and that will be considered as the answer. If we return the right peak, then we will be getting true as a output. Otherwise, we'll get false here. Uh, okay. Now, if you see the very first test case here, so we definitely have a peak element that is 8 here because 8 is greater than the element on its left because 8 is greater than 7 and 8 is also greater than the element on the right, that is 8 is greater than 3 here. Now, in the second test case, 90 is greater than 23 and 90 is also greater than 80. So 90 is greater than the elements on its left and right side. So 90 can be considered as a peak element. So we can return its index also. Okay. Now, if you see the last test case here, 1, 2, 3. So you can see here that 3 is greater than the element on its left side and on the right side there is no element. So we can imagine negative infinity there. So 3 is greater than the element on its left and in the right side since there does not exist anything. So we'll consider that 3 is the peak element here. Okay. How can we solve this particular problem? For solving this particular problem, we can apply a brute force approach. That is, we can iterate throughout the array in a linear way, and we can check for every element whether it is greater than the element on its left side and the right side if they exist. Okay. So what we will find is when we'll check for all the elements, then when we come across the element 8 here, then with respect to 8, you can see that 8 is greater than the element on its left as well as greater than the elements on its right. So 8 will behave as the peak element. So we can return the index of this particular element. So what you will do is for every element, you will take variable that is left and right, initially mark it as true, and you will check the condition for the left and the right elements. If the left element exists and it is greater, then you will mark the left variable as false. If the right element exists and the right element is greater than the ith element, then you will mark the right variable as false. At the end, both the left and the right condition should be true. That is, the ith element should be greater than both its left element and the right element. If that is not so, then we will return. Then we will move to the next index. But if for any ith index, we find that element at the ith index is greater than the element on the left and the right both, then we can simply return that particular index here. Now this approach will take the time complexity that is nothing but order of n because we'll be iterating linearly throughout the n, and the space complexity taken will be order of 1 because we are not using any extra space here. When we do this more optimally, yes, we can apply binary search and we can solve this problem more optimally. Let's see how. So what we can do is we can first of all observe some edge cases here that we had observed in the third sample test case for the problem as well. So if you see here, sometimes the first or the last element can behave as the peak. Now in this particular test case, if you will observe here, so when I'll check, so 7 is greater than 4 and 7 is the very first element. So here I can say that ARR of 0, if it is greater than ARR of 1, what does that mean? If the 0th element is greater than the element at the 1 index, then I can say that this can be considered as a peak. So if the element at the 0th index is greater than the element at the index 1, it can be considered as a peak because for the 0th element, there is no element on the left side, so you do not need to check. And if it is greater than the element on its right side, then that can considered as one of the peaks here. Similarly, this 7 also will be considered as a peak here because it is greater than the element at the index 1. Now another thing can be that sometimes the peak might lie on the right side. So suppose that the rightmost element is the peak. In that case, what will happen? If the last element is greater than the second last element, then that can also be considered as the peak condition, and we can return the last index here. If 5 is greater than 4, or you can see 5 is greater than 1 for these two test cases, this will also come under the same category here. Okay. Otherwise, what we can do? Otherwise, we can apply simple binary search. Although the array is not sorted, but we can apply the concept of binary search because we are searching in a range here. Okay, for the peak element. Now, what will happen is, suppose that we have this particular test case here, and initially my low is standing at index 0, high is standing at the last element, and mid will be standing here at the index 2. Okay, so you can see here that because the low value is 0, high value is basically 1, 2, 3, 4, 5. So the mid will be 2 here. Now, if you observe, so what is the observation in this particular test case. The test case says that the element at the mid index, it is greater than the element at the mid plus 1 index, and it is also greater than the element at the mid minus 1 index. So if the element at the mid index is greater than the element on its left and right both, it can be considered as a peak. So we can directly return the mid index. Correct. But what if that is not so? If that is not so, then what can we conclude? So in this particular case, if you will observe, so is the element at the mid index greater than both its left and right? No, it is not. Now in this particular case, for this particular test case, you can see that the mid is lesser. Element at the mid index, it is lesser than the element on the right of it. So 3 is less than 4. Okay. Element 3 is less than 4. So this means that I can try to search for my peak on the right side of mid. Why? Because this mid is not my peak. But if the element on the right side of mid, if it is greater, if the element on the right side of mid, if it is greater, then at least one peak will apply. Because the thing is that if the element at mid plus 1 index, if it is greater, so what can happen? Either the elements can keep on increasing from the mid plus 1 index till the end. In that case, 6 will behave as my peak. Okay. Or what can happen is at least one peak will lie from mid plus 1 till the end. Even if the array is not increasing like this, if they will be a, if on the right side I find an increase and then there is a dip also, even in that case I'll find a peak here. So the thing is that if the element at the mid index, if it is lesser compared to the element at the mid plus 1 index, in that case on the right side, that is from mid plus 1 till the high, at least one peak will lie. Okay, you can see that in this test case the peak will be 6, and in this test case the peak from mid plus 1 till high will be the element 4 here. So the thing is that if the mid element is there and it is lesser than the element at mid plus 1, then at least one peak element will lie from mid index till the high. So we can update the lowest mid plus 1 here. Okay, so we can start searching from mid plus 1 till the high. In the other case, suppose that what happens is, if the element at the mid index, if it is not less than the mid plus 1 element, if it is greater than the mid plus 1 element, then we can say that at least one peak will lie on the left side. So we need to update the high as mid minus 1. We should search from low till mid minus 1. That is why we can update the high like this. I hope it is very clear by looking at this test cases as well. Let's discuss the implementation also. So obviously if there is only one element, then you can directly return the index 0 here. Otherwise, you can check if the very first element can behave as the peak, return it. If the last element is greater than the second last, then the last element can behave as the peak here. Okay. Otherwise, you can say that you will start searching from the index 1 till n minus 2, because if you have checked for the first and the last element, then you will be checking inside the range. So low will be equal to 1, high will be equal to n minus 2. You will check from the second element till the second last element. Now after that, you will find out the midpoint. Okay, and if the element at the mid index, if it is greater than the element on its right and the element on its left both, then mid will be the peak here, so we can consider it. Otherwise, if the element at the mid index, if it is lesser than the element on the mid plus 1 index, so if the element is lesser, so at least one peak will lie starting from mid plus 1 till the end of the array. So we can update the lowest mid plus 1, that is from mid plus 1 index till the end, we can find at least one peak. Okay, otherwise if the element at the mid index is greater, so this means that at least one peak will lie on the left side, so we can update the high as mid minus 1 here. So this is what we have done here. Time complexity taken will be basically order of log n, because we will be applying a simple binary search here. Space complexity that we will take is basically order of 1, because we are not taking any extra data structure or any other thing. Okay, let's try and submit the code as well for this problem. So let's submit this code now. So you can see that our code is also getting accepted. I hope that you have understood this. In case if you did, make sure to comment understood in the chat. Thank you for watching this video.